All right, we are doing the 14.1 notes on random variables. So the objective, students will be able to determine the probability distribution for a random variable. So we're going to start off with a definition. A discrete random variable are variables that are finite or countable. So for example, the number of sixes when a dice is rolled 3 times, the number of babies in pregnancy, shoe sizes of a set of students. Those are all countable. A continuous random variable is a variable that can take on any value in some interval. So examples could be the height of students in a school, the time taken for a runner to complete the 100-meter dash. So in example 1, it says categorize each of the following random variables as continuous or discrete. So letter A, what do you think that is? Well, that is discrete. A is the age in completed years of the next person to call me on my phone. B, the length of the next banana I buy when shopping. Discrete or continuous? It is continuous. C is how many cats I will see before the first white one. Continuous or discrete? This is discrete. And the diameter of the donuts in the cafeteria. Continuous or discrete? It is continuous. Note, random variables are represented by capital letters. The actual measured values which the random variable can take are represented by lowercase letters. For example, if capital X represents the number of sixes when a dice is rolled 3 times, we would write the probability of capital X equals lowercase x to represent the probability that the number of sixes is x, where x can take on values 0, 1, 2, and 3. The probability distribution of a random variable represents all the values the variable can take, and it should add up to 1. So let's look at this example. Let capital X be the random variable that represents the number of sixes obtained when a dice is rolled 3 times. We want to tabulate the probability distribution for X. So on your first roll, the probability of getting a 6 is 1 out of 6. But then the probability of not getting a 6 would be 5 out of 6. That's your first roll. On the second roll, you can get a 6 or a not a 6. And again, the probability of getting a 6 when you roll the dice is 1 out of 6. And the probability of not getting a 6 is 5 out of 6. Likewise, if I didn't get a 6, I still have a 1 out of 6 chance of getting a 6 on the second one, and a 5 out of 6 on the second one. All right, then each of these has 2 possibilities for my third roll, a 6 or not a 6. So remember when we did our tree diagrams earlier this year, this is what we're using, is a tree diagram. So the probability of getting 3 sixes would be 1/6 times 1/6 times 1/6, which is 1 out of 216. The probability of getting 2 sixes here, well, you would have gotten 1/6, 1/6, 5/6, which is 5 over 216. then what I'm doing is I'm kind of going through my tree diagram. Then here I would get a 6, not a 6, and a 6. So that's the probability of 2 6s. You understand that that's 1/6, 5 6 1 6, so that is the same as before. In this part of the tree diagram, this is a 6, not a 6, not a 6. So this is the probability of 1 6. So that's 1 6 5 6 5 6, which is 25 out of 216. Then now I'm ready to go down this branch. I did not get a 6, got a 6, got a 6. So this is the probability of 2 6s. So that's 5 out of 216. Here, not a 6, got a 6, not a 6. So that's 1 6. So that's 25 out of 216. Then not a 6, not a 6, and a 6. So that's the probability of getting 1 6. So it's 25 out of 216. And then the last one, not a 6, not a 6, not a 6. That's no 6. Would be, what, 125 out of 216. So let's create a probability distribution. So the possibilities are getting no 6s, getting 1 6, getting 2 6s, or getting 3 6s. So we're going to look at our tree diagram outcomes to add this up. So getting no 6s, that was 125 over 216. To get 3 6s, remember that was up at the tippy top up here, that was 1 out of 216. Now to get 1 6, we're going to have to add a few of these together. So I have the 25, 25, and 25, which is 75 over 216. And then to get 2 6s, we've got several to add up here. I've got 1, 2, 3 of those. So that is 15 over 216. Now something I want to point out that I already mentioned is a probability distribution of a random variable represents all the values the variable can take, and it adds up to 1. This is going to be important. So I would take 125 over 216 plus 75 over 216 plus 15 over 216 plus 1 over 216. What does that equal? Well, that ends up being 216 over 216, which is 1. So that does verify that definition. Let's look at the next example and tie this together. It says the random variable capital X has the probability distributions shown. So X is getting 1, 2, 3, 4, or 5. So if I want to find the value of C, what I know is that the probabilities, when I add up all the probabilities, it should equal 1. So go ahead and solve this and tell me what you get for C. I got 20C equals 1, so C is 1 over 20. Now in part B, it says find the probability that X is greater than or equal to 4. Well, in my distribution, my probability distribution chart, getting a 4, the probability is 3C, and getting a 5 is C. So that's 4C, and we know what C is. It's 1 over 20. So the probability of getting X is greater than or equal to 4 would be 1/5. Consider the following problem. A dice is to be rolled 120 times. On how many occasions should we expect the result to be a 6? Well, if there are n trials of an experiment and an event has a probability of p occurring in each of the trials, then the number of times we expect the event to occur is n times p. We can talk about the expected outcome from one trial of an experiment. The expected outcome for the random variable, capital X, is the mean result, and this is a Greek letter mu, okay? In general, the expectation of the random variable, x, is e of x, which is going to equal the sum of all the x values times the probabilities. So back up here, n is 120, and the probability of getting a 6 is 1/6. So you would do 120 times 1/6. So you would expect to get a 6 about 20 times if you roll the dice 120 times. So let's look at another example. Each time a football player kicks for a goal, he has 3/4 chance of being successful. In a particular game, he has 12 kicks for a goal. How many goals would you expect him to kick? Well, you would take n times the probability. So go ahead and tell me what you get. I got 9 goals. All right, in example 2, x was the random variable that represented the number of 6s obtained when a dice was rolled 3 times. Here's the probability distribution. Now, these middle two I reduced. Okay, I did reduce those. It says find the expected value. Okay, well, I want you to come back up here to this formula. It's the sum of the lowercase x values times the probability. So you're going to do 0 times 125 over 216 plus 1, that's the x value, times its probability, plus 2 times its probability, plus 3 times its probability. Go ahead, use your calculator, add that up, and tell me what you get. So I got 1/2. So let's talk about what this means. What this means is if 3 dice are rolled a large number of times, we should expect the mean number of 6s to be 1/2. Okay, I'm going to include one other video here. Let me see if I can't pull this up. Here we go. All right, we're going to watch this together. And this is how you do this on the graphing calculator.
Hi, for this video what we're going to do is we're going to look at how do we find the mean, the variance, and the standard deviation of a discrete random variable using the TI Inspire.
Oops, that's the wrong one. Okay, that's the wrong one.
Hi, for this video.
Nope. Okay, hold on, guys. Let me get back to... your channel. This is not it. Okay, well, I'm going to go ahead and